When you press the K key on your keyboard, a plunger attached to the key pushes against a spring or a rubber dome. The pressure from your finger overpowers the resistance of the spring or dome so that it collapses. This causes two electrical contacts to come together and electricity flows through them, making a circuit. When you lift your finger, the spring or dome pop the key up and the circuit is broken.
How does the computer know which key has been pressed? The current flows from the key to a chip in the keyboard called a microprocessor. This processor matches the keystroke with a table of scan codes. These numbers are used to identify letters in the alphabet. The microprocessor passes this new code number onto a sort of high-tech waiting room in your RAM. That is your random access memory. RAM holds your letter until the PC is ready to use it. At the same time, the keyboard's microprocessor sends a signal to another device, the interrupt controller. It tells your PC to stop what it's doing and pay attention to the waiting keystroke. Next, the interrupt controller sends a signal to the CPU, which passes the task off to the ROM BIOS chip, which yells up to the keyboard controller, "Hey, where's that scan code anyway?" Based on what key has been pressed, the software performs some action, usually displaying a character on the screen.
A mouse lets you control an on-screen pointer to make menu selections and to manipulate graphics and text on your screen. This mouse has no feet. Instead, a small ball sticks through its underside housing. When you move the mouse, the ball moves too. As the ball turns, it rubs against two rollers and they also turn. One roller senses when the mouse moves side to side. The other roller senses up and down movements. Together, the two rollers can tell which direction you move the mouse.
Each roller is attached to a wheel called an encoder. It turns along with the roller. As the encoder turns, its metal ridges touch two fixed electrical contacts. This sends an electric pulse. The faster you move the mouse, the faster you generate the pulses. The signals from both roller encoders are sent to the mouse's circuitry. By counting the pulses and their frequency, the mouse learns how much you've moved it. Smart mouse! The mouse sends these signals through a cable, its tail, along with any electrical signals created when you press the buttons on the mouse. The electrical signals travel to your PC, where they're read by a piece of software called a mouse driver. The mouse driver now tells your software how to move the pointer on screen so that it matches the mouse's movement. And the whole process happens without any cheese.
How does the monitor work? Signals from your computer's video card are loaded into 3 electron guns at the base of the monitor. There is one gun for each of 3 colors: red, blue, and green. These 3 colors, when mixed together, can create all the colors you see on your screen. Now, these guns don't shoot bullets. Instead, they shoot a powerful beam of electrons towards the face of the monitor. The beams pass through the deflection yoke. It uses magnetism to bend the electronic beams so they can sweep across the entire screen and create the picture we see.
What happens once the beams have swept your monitor? Special chemical phosphors are painted on the inside of the monitor. Energy from the electron beams makes the individual phosphors glow either red, blue, or green, depending on the type of phosphor. The stronger the electron beam, the brighter the phosphors glow. A sheet of metal with holes in it helps keep the electron beams aligned exactly with the phosphors. This is called a shadow mask. The beams sweep across the entire screen 60 times per second. It happens so quickly that you are unaware of the firing process. Instead, your screen appears to be a steady, continuous image, just as it does now.
Software in the computer tells your printer what text or images to print and where to put them on the page. Inside the printer, a special processor powers on a tiny but precise laser light. A spinning mirror sprays the laser beam in a thin line across the print cylinder or drum. This drum is charged with static electricity and is also covered with a light-sensitive material. Everywhere the laser beam hits, it reverses the electric charge of tiny dots embedded on the drum surface. Each dot is just 1/300th of an inch wide. This charged pattern of dots will soon become a printed page. When the laser beam finishes a single line, the drum turns ever so slightly and a new line begins. Meanwhile, a sheet of paper is pulled into the printer. It passes between two rollers that give it a static charge of its own, exactly the same as that created by the laser, only stronger. As the drum rotates, it passes a bin containing a black powder called toner. The toner too has an electrical charge, but it is the opposite of that on the print drum. Since opposite charges attract, the powder sticks to the drum wherever the laser has charged a dot. Now the turning drum meets the paper. Since the paper has a stronger static charge, it attracts the toner off of the drum. Now to make it permanent, the paper passes through a set of hot rollers that press and melt the toner so it won't rub off or smear. Finally, the drum passes a charging roller which wipes off the old charge, restoring it to its original state. The printer is now ready for the next page.
Laser printers generally use PostScript and TrueType fonts. These are called outline fonts. This is because the instructions for making the font consist of only the shape of the letter, not its size or the pattern used to fill in that shape. This makes the font flexible. Software instructions can tell the printer to enlarge or shrink a character, or to make it boldface or italic, or to change the fill pattern inside the letter's outline.
The floppy drive you see here works with 3.5-inch floppy disks. They're the type most often used to carry new programs, save data, or to move files from one PC to another. The part of the disk we see is actually just the hard plastic shell. The working disk, which is inside, is protected by a sliding metal shutter. This thin inner disk, called the cookie, is coated not with chocolate chips, but with a very thin layer of magnetic material. When you slip the disk into your floppy drive, a system of levers pushes back the metal shutter. The levers also pinch two read-write heads closer so they almost touch the cookie. A motor at the base of the drive spins the cookie based on commands from your PC. The PC also signals another motor to move the read-write heads back and forth over the surface of the disk so they can read or write data. Before your PC writes data, your drive first checks the Write Protect tab in the corner of the floppy disk. If it is open, light from a tiny diode shines through and strikes a diode on the other side. This diode then says to your PC, "Don't write on this disk." But if the tab is closed, no light gets through, and the PC knows it's okay to write data.
To write data onto a floppy disk, your PC tells the drive to send tiny pulses of electricity through the heads. The pulses make the heads act like little electromagnets. Each head creates a magnetic field that reaches the surface of the disk. Remember the magnetic coating on the cookie? The magnetic field alters the tiny particles in this coating. If current runs through the heads one way, the particles are arranged with their north and south poles in one direction. But if current flows through the heads the opposite way, the polarity reverses. To read data from the disk, the read-write heads move into the same position over the cookie, but this time the process is reversed. The cookie particles create a magnetic field in the coils of wire, and this creates a current in the read-write heads. The disk drive detects this flow of electricity and passes it onto the PC. The PC translates the back and forth current changes into a series of ones and zeros, the binary language of computer data.
hard drive is where your PC stores most of its permanent data. To do that, the data travels from RAM along with software signals that tell the hard drive how to store that data. The hard drive circuits translate those signals into voltage fluctuations. These in turn control the hard drive's moving parts, some of the few moving parts left in the modern computer. Some of the signals control a motor which spins metal-coated platters. Your data is actually stored on these platters. Other signals move the read-write heads to read or write data on the platters. This machinery is so precise that a human hair couldn't even pass between the heads and spinning platters. Yet it all works at terrific speeds.
Let's look at what we just saw in slow motion. When a brief pulse of electricity is sent to the read-write head, it flips on a tiny electromagnet for a fraction of a second. The magnet creates a field, which changes the polarity of a tiny portion of the metal particles which coat each platter's surface. A patterned series of these tiny charged-up areas on the disk represents a single bit of data in the binary number system used by computers. Now, if the current is sent one way through the read-write head, the area is polarized in one direction. If the current is sent in the opposite direction, the polarization is reversed. How do you get data off the hard disk? Just reverse the process. So it's the particles on the disk that get the current in the read-write head moving. Put together millions of these magnetized segments and you've got a file. Now, the pieces of a single file may be scattered all over a drive's platters, kind of like the mess of papers on your desk. So a special extra file keeps track of where everything is. Don't you wish you had something like that?
Removable cartridges combine the speed and storage capacity of a hard drive with the ability to use more than a single disk, as with a floppy drive. Popular types include Bernoulli and SyQuest drives. A magneto-optical drive combines the advantages of a hard drive, which is based on magnetism, and an optical drive such as a CD-ROM, which uses a laser beam to read data. Optical drives can't erase or change data. They're read-only. But a magneto-optical drive gives you the best of both worlds. The high storage capacity of the CD-ROM, plus the ability to change or delete data magnetically. The drive uses a laser beam to pack data into a very small area. How can a CD-ROM disk hold so much more than a conventional disk? The CD drive reads data with a beam of light so narrow that the information can be squeezed together much tighter. You see, a laser diode creates this concentrated beam of light. The light travels through a prism. Then, through a lens and magnetic coil that focus the beam even more. On the underside of the compact disc itself are millions of tiny bumps called pits. That's right, the bumps are called pits. The same surface has smooth areas called lands. These pits and lands are translated into the binary language of bits and bytes used by the computer.
Patterns of pits and lands are laid out along a continuous spiral. As the disk turns, a precise motor keeps the laser beam in place on the path. Where the laser beam hits a pit, the light is scattered. But where it hits a land, the beam is reflected straight back along its original path. The light enters the prism again, but this time it is reflected at a 90-degree angle and strikes a device called a diode. The diode creates an electric pulse each time the light hits it. So when the laser hits a pit, no light bounces back. When it strikes a land, the diode sees the reflection and sends a pulse. These blanks and pulses are sent to the computer, which interprets them as a pattern of zeros and ones, in other words, into binary code.
Before your PC can perform anything useful, data must be moved from storage on the floppy or hard drive into random access memory, or RAM. On most PCs, RAM is comprised of modular chipsets called SIMMs, short for Single Inline Memory Modules. SIMs are designed to be easily removed or replaced in a PC. If you need more RAM, you can simply add more SIMs. Adding and replacing SIMs is a lot cheaper than throwing out the whole computer. Unlike floppy or hard disks, RAM stores information as tiny electric charges held in capacitors. This makes RAM very fast and flexible, but it also means RAM cannot store information without a constant flow of electricity. Once the PC's power is switched off, the electric charges in RAM disappear. Whatever information that was stored there is gone forever. That's why it's always a good idea to save your work to disk as often as possible.
How does RAM store information? RAM is constructed of microscopic strands etched into the silicon of the memory chip. You can think of these electrical strands as pipes, like plumbing through which electricity flows. Some pipes represent addresses, while others carry data. Now let's say we want to store the letter A in RAM. First, the PC opens a section of memory by sending a burst of electricity across the address pipe. This electric burst closes a group of miniature switches known as transistors, but only the ones needed for the data along that address line. Next, the actual information is sent as electric bursts across the address lines. Each burst is called a bit, and there are 8 bursts traveling on 8 lines, in this case to represent the letter A. In the computer's code, the letter A looks like this. Each burst travels through a closed switch and charges a capacitor. The turned-on capacitors represent the ones. The uncharged capacitors are considered zeros. Because all capacitors lose their charge over time, bursts of electricity continuously flow to refresh them.
The brain of the PC is the Central Processing Unit, or CPU. It is a complex microprocessor that consists of hundreds of thousands or even millions of transistors. The CPU is comprised of 6 main components, each performing a separate task. First, a unit called the prefetch queues up the next software instruction for the CPU. When the CPU finishes its current task, the prefetch unit asks for the next instruction. The second and third components are called the paging or segment units. They know the exact memory location of the next instruction and have it retrieved by asking the bus interface unit to send it from RAM. Say to add 2 plus 2. The bus interface unit passes the instruction along to the prefetch unit. The prefetch unit routes it to the decode unit, which translates it into a language the processor can understand. Finally, the instruction is transferred to the execution unit, which carries out the software's commands. The result is then sent back through the paging or segment units, through the bus interface unit, and finally into its correct location in the PC's memory.
We've been looking at an Intel 386 processor, a relative weakling these days. The more powerful Intel 486 processor is similar to the 386, except that it has 2 other components. One is a small 8 kilobyte memory cache. Its purpose is to squirrel away a little data or code so that it can be processed as soon as the CPU is ready. A 486DX processor also has a numeric processor unit built into it to speed things even faster. The newest Intel processor, the Pentium, has 2 memory caches, one for code and one for data. And it has 2 execution units, so that 2 separate software instructions can be processed at the same time. These features go a long way to making the Pentium the fastest chip